Welcome to this webinar on nonlinear PID control. You might ask the question, why a webinar on nonlinear PID control? Well, as you all know, PID controllers are quite common in process control. You will find a lot of these, depending on the size of the unit. It can be anything between a couple of hundred and maybe 1,000. In general, these are working very well. They're controlling pressure, temperatures, flows, and so on and so on. And like I said, most cases, performance is very good or reasonably good. Some cases they struggle a bit, and if I look at process behavior, then when do PID controllers struggle? It's mainly when processes are very slow or when there is a large dead time. If you have something like that, then typically you might want to use an APC controller, which has a much higher performance compared to PID controllers. Obviously, what's the reason to have a PID controller in the DCS? Why would you like to have it on your process? Well, one of the main reasons is it stabilizes the process. And stabilizing a process is very important for the operation. I'm saying PID controllers stabilize the process. Well, obviously they need to be tuned very well. And that's always the case. And besides tuning, also the schemes in the DCS need to be the right ones. It's like I said, PID controllers, they stabilize the process. What's the reason you actually would like to stabilize the process? Well, one of the main reasons is that to reduce the let's say the off-spec product. When the plant is steady, then you're minimizing your off-spec product, and of course that's important. I mean, if the product is not off-spec, then you have to either rerun it through the unit again or sell it at a lower price. Another reason to stabilize the process is to increase efficiency. Basically, how can you do that? Well, if the process is steady, then I can push it against, let's say, qualities against their limits. If I look at the distillation tower, if I can operate the tower at the high spec for the top and the bottom product, then typically my steam consumption will be lower. So that increases your efficiency. But obviously, if I want to do that, then once again, performance of the PID controllers need to be very high, because the plant needs to be operated in a very stable operation. Last thing, and definitely not the least reason, is proper PID control in the DCS. It minimizes disturbance propagation. What does that mean? If I have a carefully designed control scheme in the DCS and the PID controllers have proper tuning, then basically if something happens to the plant, if the process is hit by a disturbance, then the PID controllers, the control scheme in the DCS, it tries to keep it locally. So that means that disturbance doesn't propagate upstream or maybe downstream. And that definitely helps the operators, because if there is an upset, then that requires all the attention from the operators, and they have to focus on the process really hard. And if let's say if this disturbance just propagates to different areas of the plant, then that means more work for the operators, which eventually could lead to off-spec product, or even worse, a plant shutdown. So once again, it's very important to have good performance of the PID controllers in the DCS. There's one thing that PID controllers also don't like, and that's nonlinear process behavior. Almost all processes are nonlinear. Sometimes it's hurting the PID controller, sometimes it doesn't. If you would, for example, take a swing unit, which the load to this unit is adjusted based on some demand on, let's say, hydrogen or so, then you will see that the process is operated over a wide range. It has a large operating window, and it also means that the process nonlinearities you will see they are a lot higher compared to, let's say, steady state operation, always running the plant at 100% load. And it's definitely true when starting up or shutting down the plant, but typically you see when the plant is started up, then at the beginning some controllers are on manual, and let's say at about 50% load, the operator switch them back to auto, because it helps them during increasing the feed rate. And when that happens, then of course you're moving through the entire nonlinear window of your operating of the plant. The question is, how can I improve PID performance when, let's say, there's a swing unit, when the load to the plant, it changes between, let's say, 75% and 100%. I always would like to have a high performance of my PID loops. And that basically means that I'm controlling a nonlinear process. So in this webinar, I'm going to show you 3 examples of nonlinearity. The first one is, let's say, a quite common one. It's about a valve. There's also a lot of valves in your process. Typically, most of the PID controllers are actually manipulating a valve, so that's a very important one. And I'm also showing 2 examples of what I'm calling real nonlinear process behavior. But why is this real nonlinear? Because the nonlinearity in this case is not in the control element, not in the valve, but it's in the process itself. And the examples I'm using will be a pH control, which is a kind of a classic example of nonlinear control, and also a tray temperature controller, on a distillation column, and in this case a high purity distillation column. Now let's take a look at the example of the nonlinear valve. As you all know, there are all different kinds of valves. Let's say the most nonlinear one is something like a butterfly valve, which is working reasonably well between, let's say, about 20% valve opening to 40%. And if you open the valve even more, then you will see that these become very nonlinear. In the figure, you can see some nonlinearity. That if you look at the orange line, that's almost a linear valve. And if I go from the cyan up to the blue line, then basically the nonlinearity increases. Is this valve nonlinearity, is it going to be an issue? Well, it depends a bit. If the valve is always operated in the area, in the region of, let's say, 40 to 60%, then probably the answer would be no. But as like I said, when we have a swing unit where the load is increased, can be anything between 75 and 100%. That probably also means that the valve will move somewhere between, let's say, 50% and 80 or maybe higher percent. And that means that it will move through the entire nonlinear characteristic. So how can you improve this? I mean, basically, the valve is nonlinear. I'm using a PID controller, which is a linear controller. So how can you improve performance of, let's take the example of the swing unit again. How could you do that? Well, let me first, if you look at the figure, you might say, if you look at the cyan line, you might say it's not too bad after all. Maybe it's not that nonlinear, so I don't have to do anything. So what I've done in the next figure, the one at the bottom, is I've actually calculated the gain, which is basically the slope of the valve characteristic. I've calculated the gain and see how much the gain of the valve changes when I'm going from 0% output to 100%. If I look at the cyan line, which is, it has the highest gain at about 40%, which is about 1.8. But if I move to, let's say, 80% valve opening, then it drops to about 0.5, which is, it's a huge gain difference depending on valve position. Same for the pink line. I mean, that's even more nonlinear. There the gain changes from, in this case, from about 2.5 to, well, at the end, about 100% at 0.0. This is if I would calculate the ratio, it's about 30. And that also means that basically my process gain will change 30. And the PID tuning depends on the process gain. So if my process gain already changes by a factor of 30, that also means that, well, my tuning needs to change depending on where I operate the valve. That raises the question, if I have a PID controller, which is a linear controller with just one set of tuning, how do I tune this? I could tune it for 75% load, or let's say at 100% load. So if you don't do anything special in the DCS, you just optimize the tuning of the PID controller. For which valve, which operational point should I tune it then? And let's take a look at the example on this slide, which I've tuned initially. I've tuned the valve for, or the PID controller for 50% valve position, which let's say is 75% load. I've optimized the tuning, and what you see in the figure is the closed loop response. I'm changing the set point by 1, and then the red line is the PV of, let's say, a flow controller. It goes to the set point, and as it is a flow controller, it takes about 20 seconds to reach the set point. Blue is the response of the output of the valve, which is a very nice response. It shows a bit of overshoot, not a problem for a flow controller. So looks good. Fast response, good disturbance rejection. Now let's say, let's assume that the plant was operated at 75% load. Let's see what happens if you go to 100% load, which typically would mean that the valve would open. If this would be a temperature controller cascaded to a cooling flow, then and it is controlling the temperature of a reactor, let's say an exothermic reaction, then obviously the cooling valve, water valve, needs to open to maintain the temperature if I increase the load to the unit. And so let's assume the valve is now at 85%. We do the same experiment. We do a step response again, same tuning as before, but what you see now is that the performance of the PID loop is a lot more sluggish. What's the reason for this? Okay, the process gain has decreased a lot. So that means to compensate for that, I have to change the tuning of my PID loop, so increase the gain of the PID loop. And obviously performance has degraded. In the tuning for the valve position at 50%, it took about 20 seconds to go to a new steady state. This time it's probably close to 2 minutes. My simulation is not long enough. It stops at 1.3, but if you look at the red line, it still hasn't reached the set point after about 1.3 minutes. So it takes about, let's say, 2 minutes to go to a new set point again. Is that going to be a problem? Well, it depends a bit. This is a flow controller, and you might argue, okay, so what if it takes about 2 minutes to go to a new set point? It's not a big deal. Well, the thing that has also degraded is the disturbance rejection. That means that whenever the unit is hit by a disturbance, that also means it takes longer time to go back to normal operation again. And that can be a bad thing, definitely if it is, like I was saying before, it's a temperature controller on an exothermic reaction. You definitely want to maintain the temperature even if some disturbance hits the plant. And this is for a flow controller. If I would do a similar exercise for a temperature controller, which is typically slower, the closed loop response is slower. A typical temperature controller you would expect to go to set point within 5 minutes. Well, if we compare this to the simulations for the flow controller, where the time to steady state, time to go to a new set point actually changes from about 20 seconds to 2 minutes, then if I would do something similar for temperature controller, then it would take about 20 minutes to go to a new set point, which is just too long. So tuning the valve at 50% and then increasing the load, it's not a very good thing to do. So what else could you do? Well, you could tune the valve for 85%. Why not? I mean, if typically the valve is at 85% opening, then, and that's a typical load for the plant, tune it for 85%. Once again, you see in the figure, you see the closed loop response of the flow controller, set point change, and the response looks very nice. It takes again about 20 seconds to go to the set point, which is typically a good performance for a flow controller. Looks good. If I now let's say for whatever reason the operators have to cut the feed to the unit, that would mean that the valve moves to about 50%, and what happens? Well, actually, controller becomes unstable, and this is something which is very undesirable. So that raises the question: if the plant can operate between 75 and 100%, how do I tune a PID controller if the valve behavior is non-linear? Well, you could do it like this. Basically, what needs to be done is adding one block to the DCS, which is a valve characterization block. Adding this block to the valve, to the DCS, basically means that I'm linearizing the response for the PID loop. You see some DCSs, for some DCSs you have to implement an additional block in the DCS. Some DCSs already, the PID loops already supported, and you can add this characterization to the PID loop itself. The Honeywell is an example of this. You have to make sure if you do that the characterization is between 0 and 100%. If you get this characterization from a flow to OP plot, then make sure that you actually scale the flow so it is between 0 and 100% before you implement it in the DCS. Also, what's also good to keep in mind that if you plot flow against the valve position and you want to put this in a DCS, just make sure that you transpose this characteristic. For those of you guys who are used to APC controller, that's if you put a transformation in an APC controller, then you don't have to do this. But in the case of transformation in the DCS, you actually have to transpose the characteristic. And obviously you have to retune the PID loop again because the process might have changed. And last thing, it's recommended to show the actual valve position on the DCS graphic because the operators appreciate that. If they would go to the faceplate of the controller, then you actually see the transformed output, which doesn't mean it's exactly the same value as what's actually in the field. So it's a good thing to show this on the DCS graphic. So to summarize, what does it look like? Let's take the example of a flow controller again. The flow meter is obviously the PV for the flow controller. Now there is a block between the output of the flow controller and the actual valve. This is the characterization, and it's like I said, make sure that the range is from 0 to 100, and to transpose it. And just the last check is if you plot the transformed and the OP, then it should look like the figure on this slide. For higher values, you would like to increase the speed at which the PID controller opens the valve. That was the example of a nonlinear valve. Now let's take a look at, like I said, at the example of a pH control, which is it's like a classic example of nonlinear control. If you would do a Google pH control, then you will find quite some articles on how to do this. Why is this very nonlinear? Well, basically because it's the log of the concentration of the hydrogen ions. This nonlinearity can change a bit depending on if the neutralizing agent, if it's a base or an acid, and also if it's strong or weak. I mean, it can have a lot of different shapes. This is also, like I said, this is real process nonlinearity. So the nonlinearity is not in the control elements. So once again, you would like to use a transformation, characterization, but this time it's not on the valve or not on the output, but you want to put this on the PV of the flow controller. Let's take a closer look at a typical example. It's shown on the next slide. I have a stream coming from, let's say, an upstream process, and for whatever reason I would like to change the pH to, let's say, a value of 6. If this would be an acid stream, then obviously I need to add a base agent. This is typically what I would like to do. I want to control the pH leaving the vessel. I already have a flow controller on the neutralizing agent, so the question is, how can I build a pH controller which actually works? Because of the nonlinearity, it's not that straightforward. Well, the first thing I would recommend then is build a ratio controller in the DCS. And this is a ratio between the stream from the, let's say, the upstream process and the neutralizing agent. Why is it a good thing to do this? Well, the assumption is if, let's say, the load through the unit is increased, that will change the flow from upstream, and you also probably also need to increase the neutralizing agent by the same amount, by the same ratio, to maintain the pH. So you could say this is a kind of feed forward for when the feed to the plant changes. Assumption is as long as let's say I want to keep the pH at 7%, at 7, it is 7, and I change the load through the unit, and well, by moving the neutralizing agent in the same ratio, that probably would mean that pH stays hopefully close to 7. So that's a feed-forward action. Next, obviously add the quality controller to this scheme. That means cascading a quality controller to the ratio controller in this case. And as it is, a pH is very nonlinear, you also need to add a characterization block in the DCS, but this time it's on the pH, on the PV itself, and not on the output. If you do it like that, then it already works. It already improves performance a lot to compare to not having a characterization in the DCS. The main thing is that the PV for the PID loop, it's not the real pH anymore. It's some transformed unit. You could see it's more like the concentration of the hydrogen ions. It's what it looks like. So that basically means that the PV of the quality controller, it's not the real pH again. It's some different value. If I want to operate this at pH of 7, then the PV going to the quality controller will not be 7, but it might be 8 or 5. Is that a bad thing? Well, it's a bit of confusing because that also means I have to change the set point to the quality controller accordingly. So if I want to operate this at pH of 7 and the actual PV is showing 8, then I have to change the set point to 8, which might be confusing for the operators. So how to deal with this? Well, also add another characterization to the DCS, which transforms the SP to a transformed SP, which means that the SP the PID controller sees, it's in the same units, it's the same value as the PV of the flow control of the quality controller. Just to help the operators. And if you implement it like this in the DCS, then you will see it improves pH control a lot compared to just the quality control to a flow control. Let's move on to the last example, which is a temperature controller on a distillation tower. In this case, I'm assuming it's a high purity column, and on this slide you will see a typical temperature profile of these columns. I'm calling it's in the upper section or in the lower section of the column as it's flat. I'm calling it, why is it flat? Because the temperature doesn't change that much anymore. If you look at the figure, the trace 1 to about 15, temperature is almost constant, and the same holds for the top section of the column. You would like to have a temperature controller on these columns because controlling the heat balance of these towers is very important. So you really need a temperature controller to stabilize column operation. The problem is you would like to have the temperature, the thermocouple should be located at the tray where the temperature gradient is the highest, the largest one, because that's the most sensitive tray of the column. But if you have that, then you will see that, and you have added something in your plant, and you will see that these temperature controllers typically are struggling to maintain set point. These temperature controllers cycle a lot, they show sluggish behavior, and so on and so on. And it's not very easy to tune these. it's definitely, you see that these are struggling when the feed to the column is changed. But what's the reason for that? Well, let's assume you're tuning this temperature controller. You're doing an open loop test. Ask the operator to put the temperature controller on manual and then change the output of the temperature controller. Just to see how the process responds to that. What you see is that you only have to ask the operator to change the reboiler steam. That's the assumption. Temperature controller is cascaded to reboiler steam. You only have to change the reboiler steam by just a few kilograms, and then you will see that the temperature already starts to change. If I increase reboiler steam, ask the operator to increase reboiler steam a bit, then you will see that the whole temperature profile starts to shift up. And if you're looking at a trend on the DCS while you're doing that, then you will see the temperature starts to go up and increases, and you ask yourself the question, will it ever stop? Well, what's the explanation for that? It's like I said, I mean, the heat balance of these columns is very important. If you just add a little bit of steam to the reboiler, then it shifts the temperature profile up, and basically the temperature keeps on changing until it hits I'm saying the flat profile again, and then it stops. So if you do make a small step on the reboiler steam, then you will see temperature starts to go up, and it might change 10 to 20 degrees, and then it's steady, and it doesn't change anymore. That's typical process behavior of these columns. That also means that once it has reached the flat temperature profile, it will not change anymore. So if the thermocouple is now measuring the flat profile, then you will see if I would increase steam again, then nothing will happen, temperature will not change again. And this is where the nonlinearity, you'll find the nonlinearity. I mean, if the temperature profile shifts too much up or down, then basically the response, it's dead. It doesn't change to steam anymore. And that's a bad thing for the PID loop, because the PID controller always assumes a linear process response, which is in this case not the case, in this situation not the case. Well, if I would do something similar but now decreasing the reboiler steam, then you will see a response like this. Now the temperature profile shifts down, and once again it reaches the flat, the thermocouple reaches the flat temperature profile, and once it's there, it's not going to change anymore. So same question again, how can we improve performance? Well, you could do it like this. If there are 3 temperature thermocouples available in the DCS, then you could calculate the average of these 3. And the average of these 3, they will be the PV, the process value for the temperature controller. So the temperature controller in this case is not going to control just 1 thermocouple, but it will be the average of 3. Like I said before, these columns are very sensitive to feed changes. So it's the best approach in this case is also very similar to pH control, is to build the feed forward, but for the feed, which means add a ratio controller to the DCS, which is the ratio of the reboiler steam and the feed, and cascade that one to the reboiler steam flow controller. Once again, the assumption is if the feed to the column increases, then I have to increase reboiler steam to maintain the temperature. And the feed forward action of this control scheme already takes care of that. And hopefully, if you do it like that, then the output of the temperature controller is basically just a trim of the ratio. That means it will make the life of DC a bit easier, and you will get a better performance. So the final solution is build a ratio controller in the DCS, which is cascaded to reboiler steam. The ratio controller controls the ratio between reboiler steam and feed, and then next cascade the temperature controller to the ratio controller. And the PV of the temperature controller, this will be the average of the 3 thermocouples, which what happens, why would you like to do this? This widens the range, the linear range, operational range of this column. And of course, last but not least, once again you have to retune the controller, and this time you really would like to tune it for disturbance reduction, because of the flat, the steep temperature profile, you still see that this temperature controller is struggling to maintain temperature, and tuner for disturbance rejection is the best solution in this situation. That was my last slide. Christian, back to you.
Okay, thank you very much, Arthur. So in the meantime, we started also our Q&A session, which means if you have any questions, please use your chat window to the right of your WebEx screen, where you can enter all your questions. And so in the meantime, some of these questions came in. I'm going to collect them a little bit, and then I will ask Arthur to respond to them. But perhaps, Arthur, since we are, well, can you go to your previous slide, please? Because I have some questions that came in regarding this slide over here. So about 3 questions. Let's start to address them. So for valve and pH example, a characterization block is used, and why not also use a characterization block for trade temperature control?
That's a good question, and the main reason is that for the valve characteristic, the assumption is the flow to valve characteristic will not change that much depending on the process condition. It has kind of a fixed shape, you would say. Well, if I look at the temperature profile in the column, that might change depending on the separation index. It might change when I increase or decrease the reflux. That will change the shape of the temperature profile, and that basically means that I cannot use a fixed characterization for this because it depends on the process conditions. And taking the average of the 3 temperatures is working better than, because then it really uses the real process values all the time, and it doesn't depend that much on the shape of my temperature profile.
Okay. So immediately connect to that question, this one here, okay, you talk about 3 temperatures, assume you only have 1. So you only have one of these, so you don't have these 3 measurements on that slide, but you only have 1. So can you at least do something then to improve it or not?
Well, that's a good one. I mean, basically what you have to do then is make sure it doesn't, the profile doesn't shift that much up or down. And if you have only 1 temperature thermocouple available, then obviously you cannot use the average calculation. Well, the best solution would be add 2 additional thermocouples to the process, but sometimes that's very difficult. So if you have only 1 available, then what you should do is still build a ratio controller between reboiler steam and feed, because that's a feed forward action and that already helps. And then give the TC some very aggressive tuning. So basically the TC will make sure, the temperature controller will make sure that the temperature profile doesn't shift that much up or down. So you never get into this nonlinear operating region, and trying to avoid that. Will it be always the case that the temperature controller keeps it in the more linear operating window? Well, probably not, but it will improve performance already.
Okay, good. And then the last question about this slide that came in is about your last item there, tune temperature controller for disturbance rejection. So the question is, how?
How do you do that? Well, if you look at, once again, if you look what happens if you increase, for example, reboiler steam, you're doing open loop test, ask the operator to increase the steam. What happens if you start trending the temperature, and you see this temperature keeps on increasing. I've seen situations where the temperature increases by 10 degrees, sometimes 10, 20 degrees, just by changing the reboiler steam by 200 kgs. 10 degrees is a lot, and you always wonder what happens if I increase steam and I wait for, let's say, 20 minutes, and I see the temperature go up at 20 degrees. What happens to my top product, like an off-spec? So if I don't wait that long enough to reach a new steady state, then increasing steam, reboiler steam, means temperature will go up. But before, let's say it increases by 5 degrees, and then I step the reboiler steam down again. And that looks a bit like a level controller. And that's also how you would like to tune these temperature controllers. Don't tune them as a steady state controller, like a temperature controller, but tune these very similar to a level controller, because basically that's what the temperature controller is trying to do here. It's balancing the temperature at set point. And tuning a level controller means I want to give the TIC, the temperature controller, a high gain, high proportional gain, and a very low integral action, so a large DI. And that's also how you tune it for disturbance rejection, so tune it like a level.
And ask PID tuner or Aptitude to do it for you.
And of course, you ask.
Of course. Good. Please send more questions. We still have some time left, so use your chat box on the WebEx to provide some more questions or send some more questions for Arthur. And there is one regarding the pH control. For pH control, you need a characterization. So yeah, how can you find that? So perhaps.
That's a bit of a tough question. The best way to find this is if you would have a regular simulation of your plant.
Mm-hmm.
You do a simulation, a sensitivity analysis, or case study in HYSYS, for example, and then you will find your characterization. You could also try to extract it from plant data, which is not that easy, but if you don't have a regular simulation, then that's how you should do it. And what also helps is if you have any modeling software, let's say you do with APC controllers and you have a modeling software to build the APC model, try to model for example the neutralizing agent flow or the ratio, try to model this against the pH. That will give you a linear model and then plot the prediction of the model and the actual pH measurement, plot these against each other, and that will give you the characteristic very similar to what you could also do for, let's say, nonlinear qualities. If you have a distillation tower, you want to control the top quality in an APC controller, which is top quality is nonlinear. That's also how you build a transformation for an APC controller. Plot the predicted value and the actual value against each other, and that will give you the characterization.
Mm-hmm. Okay. One other question regarding pH control. Suppose you have a buffer in pH control which shifts from run to run and therefore also responds to flow depending. Is characterization block still the right solution or are there other tricks available? Wait, let me Arthur read the question again.
The question is, suppose you have a buffer in the pH control which shifts from run to run, and therefore also the response, depends on the flow. Is the characterization block still the right solution, or is there something else you could do? Well, that's always a problem. This would happen, for example, if the flow to the unit changes. That means that the flows will change, and you will get all these kind of non-linearities. I would still recommend using a characterization block in this case because it will definitely help. I mean, it's not easy to also compensate for flow changes, basically, and that's not an easy thing. And for all these control schemes, it's better to have something simple, which might not be perfect, but have something simple in a DCS, which already helps a lot, instead of including something that's very complicated, and because it's very not easy to get it working and working under also when, for example, an upset happens. And you have to make sure that these controllers will be able to handle upsets, and the best way to do that is by keeping it simple in the DCS. So the short answer would be yes, it still helps to have a characterization block, and just make sure that the tuning of the quality controller is such that it can handle these flow changes.
Yeah, okay, so make it very robust. So perhaps can you go to the slide which I'm having here? Because there was a question regarding a certain slide on the nonlinear valves. So hold on a second, and then I will raise the question. Yeah, okay, this is the one. The question here is, why is in the second graph the output responding less aggressively? I can understand the PV that is quite sluggish, but why is the valve opening less with the same tuning, so less aggressive? So,
it's basically this thing is not running. The controller game is too small here. Yeah. So it's only integrated. It's only the integral action which takes care of this. And as you might see in the plot in the top section of the slide, you will see that the proportional action is very important for this flow controller. Yeah, and that's the thing that's actually very low for the bottom figure, and that also means that my controller is a lot more sluggish. It's the initial kick of the output that helps a lot, which is in this case there is an initial kick, but it's too small. And why is it too small? Because my process gain is a lot smaller now.
You tuned it for a very high gain, and now you get a sluggish controller because it runs on a very slow.
Yes,
slow gain
yeah.
process. Yeah. Okay, so time perhaps for a last question. That's again about pH control. It's an I think a clarification on the question that was raised before. The change is a product property which results in large differences in required chemicals for the same pH.
That's true. That's true. So
perhaps I don't really understand the question completely, so perhaps you can first tell what the question.
It's like I said on this slide. It's the process response depends on if it's a strong or weak acid base. So that also means if my stream from the process changes, that might change my characteristic depending on how the plant is operated. And it's absolutely true that if I'm using a fixed characterization, then basically I'm ignoring that. This means that if you use a characterization, it will always be an average characterization of all operating points, and we are assuming that will be sufficient. Changing the characterization online is not an easy thing to do. And basically it's you have to take care of this by making sure that the pH controller is not tuned too aggressive, so it still can handle these, let's say, mismatch of characterization. That's how you should do it.
Okay.
Basically detune the quality controller a bit.
Yeah. Okay. So I think that was the last question, but in case you have more questions, please, you can always send them to me via email, and I will ask Arthur to respond directly to you so that you will get a personal answer from him. So first of all, thank you for your participation. In case you want to have the slides, and I also saw that some people asked for the slides, no worries, just send me a quick email and I will provide you the slides in PDF format. If you want to look again, watch again the webinar, it is being recorded, so by tomorrow, latest on Thursday, on our YouTube channel, you will have a recording of the webinar so that you can have a look at it again, or you can also, of course, and I hope you do, share it with your colleagues and your friends. And I also want to take the opportunity now to announce the next webinar, which will be held in April. The date is still to be decided upon, but you will be all invited. And that is about simple and effective KPIs to monitor and maintain APC controllers. It will be given by Sam Dallowell. And Sam wrote me the following abstract, which I'm going to read to you, is the benefits arising from the implementation of APC are not always well understood. It is also difficult to articulate and communicate these benefits to the management as well as various stakeholders at an operating facility. In this webinar, we will share our experience with KPIs related to APC and some best practices related to choosing and calculating them. So I think it is worth attending again the next webinar, which will be held in April. But again, you will get an invitation to attend. So for the time being, it's now about 20 minutes past 12. So we will stop the webinar now. And again, if you still have some questions remaining, please send an email to me and you will get a personal answer. But for the time being, thank you very much for attending. Thank you also very much, Arthur, for presenting. I hope to see you or hear you again at the next webinar. Thank you very much, and bye-bye.